Okay, let's have a sort of a reality check. What have we been doing and so what? The last few sessions have been talking about X-ray production, and specifically, we've been looking at what are the factors that you manipulate to produce your image. Those are important. You have to know when you change these various factors, they're going to affect your image. They're going to affect patient dose. So we've been going down the line, identifying all the parameters that you have to set to produce an X-ray image, and then defining all the results of changing those parameters. And so far, we've looked at what if you change exposure time? What if you change MA, the milliamperage, which is a measure of how many electrons are going across the tube? And then we ended up last time with this idea of the MAS, the mass product, the product of the milliamp and the time. And all three of those parameters, time, MA, and product of MA and time, all follow a curve as shown over here. They are directly proportional parameters. Here we show going from 100 MAS to 200 MAS. So what do you do when you change, when you double the exposure time, the MA or the MAS? You double the number of photons at every energy level. You don't change the energies. It's still the same Emax. It's still the same E effective, but you do change the quantity. And this is what you see over here. And I've also taken the opportunity to define some of the terminology. In beam quantity, sometimes we talk about output, intensity, number of photons, exposure, air kerma. These are all measures of how much radiation comes out of the tube. And, and then if you have twice the amount of radiation, like you would if you doubled your parameters, then you get twice the dose. The patient dose is directly proportional. Uh, the fact that you have more radiation, you have less noise. We're going to be talking a lot more about noise. I showed you examples last time, but right now, emphasize indirect proportionalities. If one goes up, the other one goes down. If the number of X-ray photons goes up, then the noise goes down as indicated with this arrow over here. However, if you're still in the old-fashioned film modality, more radiation means that the film gets blacker. Its film density gets greater. The beam quality is a measure of penetration and transmission. And we saw terms like half value layer, 10th value layer, TVLs and HVLs. We use the expression of hardness. How hard is a beam? When you ask that question, what you're asking is, how hard is it to filter the beam? How hard is it to remove photons from the beam? High energy beams have, we say, are very hard because high energy photons will get through pretty much anything you put in their way. Okay? Likewise, there's a soft beam. Mammography deals with soft beams. Soft beams are relatively low energy photons. And if they're relatively low energy photons, you know that they have very poor penetration. They don't get through, very poor transmission. And then the subject contrast. Uh, subject contrast goes as energy. But we've just seen that energy is flat. So subject contrast does not change. Okay? And the only time that you'll have a motion problem with changes of MAS if you change the time. Motion is always related to time. It is not related to the MA. Well, enough said for that. I've seen these before, shown the little calculations before. But now let's go to KVP. Everything changes dramatically with KVP. Little changes in KVP produce big changes in everything else. What do we mean by KVP? Kilovoltage peak. You have a particular voltage across the tube, and that's the voltage that's going to accelerate the electrons across the tube. And we measure that in thousands of volts, and some test films go up to 120 kVp. CT scanning goes between 120 kVp and 140 and even higher kVp. While the lowest kVps, as you well know, is down in mammography, where typically there you're talking about maybe 25, maybe between 25 and 30 kVp typically. Okay, but so what? What does that determine? It determines the energy with which the electrons bombard the target. It's the accelerating voltage. It's the voltage that gets the electrons to move faster and faster and therefore pick up more and more kinetic energy, energy by virtue of motion. And the higher the energy, then the more interactions it can undergo in the target. That's this last item on the slide. And if you have more interactions, you produce more X-rays. And those X-rays are typically of higher energy. So let's see what it would look like looking at the Bremsstrahlung spectrum. Here you have, let's say, a 50 kVp beam. 50 kVp defines an Emax of 50 keV. The average or effective energy would be 1/3 of that, 17. And remember, that's the average at the surface of the patient, incident on the patient. Well, let's double that to 100. What would it look like? This is what it looks like. Notice that if you change the kVp, you're going to change the Emax. If you change the Emax, you're going to change the E effective. So now you have a totally different set of numbers. And as you look at and compare these two curves, notice that both the quantity and the energies change when you change kVp. That wasn't true when you changed the MAS, the MA, and exposure time, but it is true when you change the voltage. And little changes in voltage, we're going to see make big changes in everything. Okay? So let's go down the line and look at the features of what happens as you change the kVp. Well, if you have a higher kVp, obviously from the curves, you have more output. There's more photons, X-ray photons being produced at every energy level. How come? Well, as we mentioned before, if you have a higher kVp, the electrons acquire more energy, and if they acquire more energy, they can produce higher energy photons and more of them. So the outputs all go up. Well, if the outputs go up, then the patient dose will go up, right? For all else the same. If you just change the kVp on the machine, you automatically get more radiation, and therefore your patient dose is going to go up accordingly. Okay? Now, here is a point of much confusion, and we're going to be discussing it a little bit later on. I'm going to put this aside, but look at this statement. I just finished saying that the patient dose goes up. Well, you can manipulate things so that you end up having less dose, okay? And I'm going to explain what we mean by for the same image effect. I'm going to explain what we mean by for all else the same, okay? But for now, we're going to come back to the second dose parameter where it goes down. But for now, I do appreciate that the dose will go up if, in fact, you go up in kVp. And as we've seen, you get more photons at all energies, okay? How about the image effect? Well, if you get more photons, less noise. If you get more photons, the film gets blacker, okay? We've seen that before. How about beam quality? Now, remember, beam quality goes as energy. The penetration goes as energy. Well, when you change kV, you change energy, as we've seen in these curves here. So if you have a higher Emax, a higher effective, that means a more penetration, more transmission, larger half value layers and 10th value layers, and the beam is harder. And over here you see that on the yellow curve you had 17, but when you went to 100, 1/3 of 100 is 33, so you've gone up in both Emaxes and E effectives. And then subject contrast. Subject contrast goes with energy in the opposite directions, so that as your beam energy goes up, as it will with kVp up, then subject contrast goes down. Okay, and we'll be explaining this statement as we go along. But essentially, if for no MAS change, okay, and for the same noise, we have to discuss that a little bit further. Okay, but let's now look at this the rationale for the beam quantity and come up with a very important conclusion. We've already said that the accelerating voltage is is responsible for the kinetic energy of the electrons, and you have more energy available for X-ray production. But now, an important observation. This has been on pretty much every board exam in the last few years. How does the output vary with voltage? See, when we talked about MASs and MAs and times, it was directly proportional, but not so with voltage. It's a quadratic function. It goes as the square of kVp. The square of kVp, it goes as the change in kVp squared. Here I've shown a delta R, a little discussion on that, or a little statement on that. When you had mathematics, calculus and whatnot, you use delta to always indicate a change, right? And typically in calculus, it was a subtractive change. Remember, y2 minus y1, x2 minus x1. We use a subtractive change for the characteristic radiation energy production. Remember that? To produce characteristic radiation, an electron will transition between two orbital binding energies, and then the difference, the subtractive difference, comes out as characteristic radiation. Remember that? The binding energy of one minus the binding energy of two, of the second one. Now, it is very common in radiology not only to use a subtractive a change, but also a ratio change. What do I mean by a ratio change? It's right over here. Rather than say, well, the first kV minus the second kV, we put the final kV and we divide the final kV by the initial kV. That's what I mean by a ratio. R stands for ratio, a difference. And that ratio difference is squared. Okay? Example, I gave you the curves for 50 kVp going up to 100 kVp. Well, 100 over 50, that's 2. 2 squared, 4. In other words, now, if you double the voltage, you will get quadruple the output. And if you get 4 times more radiation incident on the patient, now the patient will get 4 times more radiation. And if this is fluoroscopy, if the patient gets 4 times more, you get 4 times more. Remember that little rule in fluoroscopy? Your dose goes directly proportional to the patient dose. Double the patient dose, double you. In this case, quadruple the patient dose, quadruple the dose to you in fluoroscopy. Okay, but now let's go back to that second statement on dose. Remember, I mentioned there was 2 possibilities. First of all, when your kVp goes up, the dose goes up. That one is straightforward. A kVp up means you get more radiation. More radiation, patient dose goes up. Okay, but now, how about this one? For the same image effect, we're going to have to talk about that. For the same image effect, if you do 2 things, number one, you go up in kV, but then you go down in MAS, then you invariably end up with less dose. I'm going to illustrate that. But right now, I just want to give you the words, and then I'll give it to you more graphically. The second possibility here, where the patient dose goes down, which is an extremely important observation for us, if you have a higher kV, we just said you have more penetration. But wait, stop right there. If you have more penetration, that means that you're delivering more radiation to the image plate. If you deliver more to the image plate, then you don't need as much up front. You just lowered the dose to the patient. Let me show you that in a graphic. Here's a patient, and the typical transmission of radiation. This is the one I want you to take home. The typical transmission at typical kVs for typical patients. You get 100% dose at the surface, and then you get less and less radiation getting through to the middle of the patient, so you end up with only 10% of what you started out with at the surface. And finally, at the exit, you get around 1%. Remember 110 1. We rounded this out so it's easy to remember. The 100% gives you a skin dose. It's right at the surface of the patient. The 10% is a good indicator of female fetal dose, the fetal dose. And we're always interested in determining fetal doses. You can take, as an approximation, 10% of whatever the skin gets. The exit dose, 1%, we use to calculate what gets through to the image plate. If you have 100% at the surface of the patient, only 1% gets through the patient and arrives at the image plate. Okay? So 110.1. But now let's go to an even higher kV. If you have a higher kV, you have more transmission. So again, we always define 100% at the surface, but now with the higher penetration, maybe twice as much. I'm just coming up with a number. Twice, let's say, twice as much radiation arrives at the middle of the patient and twice then exits the patient. Well, so what? Let's put some more numbers on this. Typical image plates require about 1 milli-R of exposure. 1 milli-R of exposure. Well, if you want to deliver 1 milli-R to the image plate and the image plate is only receiving 1% of the entry dose, that means you have to give 100 MR to the entry skin, right? 1% of 100, you've got 1 MR. You've got enough radiation to give you a decent image plate. All of our image plates in radiology and radiography pretty much fall between a half an MR and 1 MR, between a half and 1 MR. So we have a decent image at the typical kV. Now, let's decide to go to a higher kV with the greater transmission. If you gave 100 MR like you did in the prior case, now you're going to get twice as much arriving at the image plate. Too much radiation. You only needed 1. But now, because of the greater penetrating ability at the higher kV, you've got 2. 2% of 100 is giving you the 2 MR. Well, what do you tell the technologists? Go back and lower the dose. Cut the dose in half. So he goes back, and instead of giving 100 MR to the patient at the skin, he gives 50 MR. 2% of 50. Now you've got your required 1 MR. The image plate will produce a desired image, but it produced the image at a lower dose. There's your example there. And when you match the exposure to the image plate, we are actually matching. If it was a film, you'd have the same film density because you've got the same amount of radiation arriving at the image plate. So your film would have the same degree of blackness. How about the noise? It would have the same amount of noise because you've delivered the same amount of radiation. You've delivered approximately the same number of photons. So it'll have the same noise. Remember, noise goes as how much radiation arrives at the image plate. And so you've matched the noise, you've matched the film density. So under these cases, when you go up in kV, dose goes down. Dose goes down. One of the ways that we can reduce dose to a patient is by going up in kVp. Going up in kVp, again I repeat, increases penetration, transmission, more radiation at the image plate, less radiation incident on the patient. Okay? So that we have those two possibilities. And I'll give you another visualization of what we're talking about. Assume that you're walking up to an X-ray machine. You grab the handle that controls the kVp and you up the kVp. And you do nothing else. Do nothing else. Just up the kVp. You just increase the dose to the patient. And it goes as a voltage squared. Remember that little ratio squared. Okay? Now visualize another scenario. You go up to the X-ray machine. You up the voltage with one hand. And get this, with the other hand, you lower the MAS. Lowering the MAS then allows for the lower dose. You have to do two things, up kV and then lower the amount of radiation incident on the patient. And you lower it to the point that you end up with the same amount of radiation at the image plate, the same film density at the image plate, the same noise at the image plate. You match number of photons arriving at the image plate. Okay. This is I've shown this before. It's a picture of the photo timers. I thought I'd put this over here. Remember that the machine turns itself off when it has the correct amount of radiation at the image plate. Hey, this is what we've been talking about, the appropriate amount of radiation arriving at the image plate. When you're in phototimers and you go up in kV, the machine will automatically turn itself off at a lower MAS value because the role of the AET, automatic exposure termination parameter, sometimes also called the AEC, but most popularly called the plain old photo timers. When you have photo timers, the role of the photo timers is always to turn the machine off at the appropriate image value, at the appropriate number of photons arriving at the image plate, at the appropriate film density, at the appropriate amount of noise arriving and being registered at the image plate. Okay, so it assures that if you do go up in kVp, you automatically reduce the exposure time or the MAS, and therefore you automatically reduce the amount of dose. Okay? Okay, so here's a summary then. We've already seen that as kVp goes up, the dose will go down for the same image effect, same noise, same film density, but you have to change the technique, the MA, the MAS, or the time. If you're doing the AET, the photo time that's done automatically. The tech doesn't have to give that a thought. Okay. However, the dose will go up if you have no other technique change. Okay, no other technique change. But typically, you always have AET or photo time misfunctioning. So typically, the dose will always go down, okay, because your AET will assure that you always get the correct change to give you the correct image at a lower dose. Okay, let's look at some importance of kVps then before we move on. Remember that kVp determines the penetrating ability of the X-ray machine, and it also determines how much radiation is being produced, right? Higher kV means more radiation produced. Patient dose is going to be affected by photon energies over here, as we've just discussed. And how about subject contrast? Remember that subject contrast was a function of how distinguishable the tissues are. Now notice, if you go up in kVp, good result is patient dose goes down. Bad result is subject contrast goes down. Remember, subject contrast always goes in the opposite direction of energy. If energy goes up, then subject contrast goes down. Here's putting together all the ideas that we've had up to this point in terms of a quantitative relationship. I give this to you like I gave those other little equations out of interest. But remember, you know the proportionalities. You don't need math. If you double the MASs, you double the outputs. Final outputs will be twice as much than what you started, the initial outputs. But now remember the ratio change of voltage. If you those go as the ratio squared. So just take the final divided by the initial, square it, and that's how much more output you will have beyond what you started with. Okay, and here's an example. If you start out with 10 MR and you go from 50, you start out at 10 MR, which were obtained at 50 kV and 50 MAS. If you go to 100 kVp, 100 MAS, just looking at this, 50 to 100 is a factor of 2. Squared is 4. So 50 over 100 over 50 is 2, but those are just directly proportional. So you have a 4 from the kV, you have a 2 from the MASs, and that result is 8. Okay, let's do it the long way, where you had the initial output was 10, and then the ratio of the MASs, that's a factor of 2, this factor of 2 here, and then the ratio of 100 to 50 squared, there's your factor of 2 squared, and finally 8 times more skin dose. Okay. Okay, let's move on. Enough said for kVp. Let's go on to filtration, another parameter. Now, this one I've put as a technique change, but in the USA, we are pretty much using a fixed filtration. We typically don't change filtration in radiography. We do change a filtration in fluoroscopy. That one is done unbeknownst to you. the machine decides to put in extra or less filtration. Remember in mammography where we talked about matching the filters to the target material, and that you had like a little filter wheel so that the filter wheel rotate to bring to bear the appropriate filter, whether it was molybdenum or rhodium or whatever. Okay, let's talk about filtration. And here, go back to the X-ray tube, the housing, the collimator. And of course, remember that the X-rays from the target have to go through the glass envelope. They have to go through the oil. They have to go through the mirror in the collimator. So we have one source of filtration, which we call the inherent filtration. That's due to the tube housing, the glass and the oil, what's happening inside the tube housing, the enclosure given by red over here. And then we have the collimator filtration, mainly the mirror, okay? But the radiation has to go through that before it leaves the collimator and arrives at the patient. And then the third parameter is a lot of our systems have the facility to add filtration. That filtration is usually placed between the tube and the collimator. The tube is in yellow, the collimator is in white. So typically, down in here someplace, you would put that filter. But as I said, in the U.S., we typically don't use filtration in radiography. In Europe, the technologists like to use filters, and they vary the filter depending on the needs of the patient. Typically, we don't do that in the USA. We work with fixed filtration, typically in radiography. But let's see what happens when you add a filter. Take a look at the curves of comparison. The red one is before you put in the filter, let's say, and the yellow one is after the filter. Let's make some very important observations. Okay. First of all, notice there's fewer photons, right? Well, that's what a filter does. A filter filters out photons. Okay, so that the outputs go down. Okay, the air currents go down, etc. Now, notice, however, a very important statement. Yes, there is removal of photons, but it's preferentially at the low energies. It's the low energy photons that are more likely to be absorbed rather than the higher energy photons. Well, that's intuitive, isn't it? High energy photons tend to go right through given materials. They are harder. So in a typical X-ray beam where you have both hard radiation and soft, the soft being the low energies, the hard being the high energies, then it's going to be the low energies, the soft radiation, that will be preferentially absorbed in that filter material. Okay, very important idea there. Preferential absorption at the low energy components. Now, there's going to be an absorption at all energies, but the higher energies will be relatively lower significance in removal of attenuation. It's mainly at the low energies as shown by these curves over here. Well, if you remove photons, your patient dose is going to go down, right? Now here we don't have a good rule of thumb. We don't have a good rule of thumb for the beam quantity going down. And I remember we saw that changes in MAS time was directly proportional. Changes in voltage was as a square. Well, we don't have a nice, convenient rule of thumb for either beam quantity or patient dose, but it does go down, and I think that's pretty intuitive. But if you have less radiation, you're going to have more noise, right? And the film density will not be as black because you don't have as much radiation. How about the beam quality, the energy? Notice I've drawn in these dash curves, lines rather, and the energy effective has gone up. Well, if you remove the low energy components of a beam, what's left is higher energies, and the average energy is going to go up. So your beam quality goes up, your penetration, your transmission, your beam hardness, all go up. And if the beam energy goes up, subject contrast always goes in the opposite direction. And if subject contrast goes down, and because you have less radiation, you got more noise. Okay, as we've seen back at the image effect, more noise, okay, because there's fewer photons. And how about motion problems? When you filter a beam and you have less radiation, now what's going to happen is that you're going to compensate by extending the exposure time. And by extending the exposure time, now you kick in motion problems. Okay, okay. What's the importance of this? We got to go back to this, the fact that we've seen that the preferential absorption of low energy photons. Why, that means that we can use this as a handle to reduce patient dose. Remember that it's the low energy photons that are more likely to be absorbed inside the patient. The patient serves as a as a uh, as a big filter. Okay? But let's go down the line. We know that the energy distribution is affected by the filtration. The penetration of the beam is affected by the filtration. The contrast is affected because filtration changes energy. And if you change energy, you change contrast, and they go in opposite directions. And then I wanted to especially emphasize the patient dose. We'll talk about that right now. But notice the little note I have at the bottom of the slide. KVP and filtration, you can't, it's very hard to separate one from the other. In practice, they always come together. They always form a duet. And you can affect energy by playing around with KVP, and you can affect energy by playing around with filtration. Okay? So that, for instance, theoretically, if I go up in KV to increase my energy, I can take out filtration that'll exactly match that increase in energy. See, if I take out filtration, the beam becomes softer. Higher KV makes the beam harder. Higher filtration, a lower filtration makes the beam softer. So I can go back and forth, and I can, if I decide to go up in KVP, but I want the more or less the same penetration, I can go down in filtration and sort of match them. So they always come together. You can always work them together as a duet. Okay, an increase in KVP can be offset by a decrease in filtration, as I just mentioned, to get the same penetration, the same average energy, or the same half value layer. Likewise, an increase in filtration can be offset by decreasing the KV. Same idea, but working with the other parameter. What's really important then is always, what's the average energy? What's the half value layer of the beam? So that's the important parameter, because you can play with KVP, but that can be offset by playing in the opposite direction, the filtration. So what's important is the effective energy and the half value layer, the transmission, the final penetrating ability of the beam. Now, I mentioned that this was going to be important for patient dose. Let's look at that. This idea of preferential attenuation at low energies. As we saw, as you add filtration, you're going to get rid of the low energies, and you end up with a higher energy average. And well, let's now see how that affects dose. Okay? Here's a patient. There's your X-rays. Let's say that those X-rays have both the low energies and the high energies, and they start going through the patient. Now, what happens to the low energies? Preferential absorption of the low energy photons. They'll be absorbed in the shallow layers of the patient. They will not be able to penetrate. They just go to patient dose. So a strategy is, let's pre-filter the beam. Let's filter the beam and remove the low energy photons before they get to the patient. There's our strategy for patient dose reduction, okay? To offset the fact that if you allow these soft radiations to hit the patient, they'll just go to dose. They won't particularly add to the information in the final image. So we pre-filter the beam for one sole purpose, to reduce the skin dose. This is so significant that our machines, by law, have to have a minimum filtration. Take that number home with you. 2.5 millimeters aluminum equivalent. You got to have that minimum. You can play with all the filtration you want, but there has to be that floor, that minimum to assure that you don't have those very low energy components hitting the patient. Okay? Well, let's look at some typical filtration values in reality. The inherent filtration typically goes between, and you don't have to particularly remember these numbers, just the concept that we're going to be developing here. The inherent filtration goes between 0.5 millimeter and 1 millimeter. And look at the way we express filtration. Aluminum equivalent, aluminum equivalent. Remember, inherent filtration was the oil and the glass. There is no aluminum there, but yet we express their thickness in terms of the equivalent amount of aluminum. The collimator filtration typically goes between 1 and 2.5. So if we add these, notice that if you add a tube with a 0.5 and a 1 combination, well, you end up with 1.5. You will not meet the required minimum of 2.5. Okay? So what do? You add 1 millimeter in addition to that. Now you have a sum of 2.5. It is the role of the physicist to periodically go by and check your machines to make sure that they have the correct amount of filtration. What if you had a machine that had the 1 millimeter inherent and 2.5 collimator? Well, right there you have 3.5. You have more than exceeded or met the minimum of 2.5 millimeters of aluminum equivalent. Most physicists will shoot to have their machines between 3 and 3.5 millimeters of aluminum equivalent. Remember, the 2.5 is a minimum. It's a little bit better if you have a little bit more. Okay? A little bit better in terms of your dose to the patient. So, but you're shooting for the range of 3 to 3.5, but you got to meet that minimum of 2.5. Okay? This filtration, when the machine is first manufactured, they do this, they make sure that it's there to meet the federal minimums, and then the physicist, upon installation, will make his checks and make sure that you meet that minimum. In Europe, techs often change filtration as per needs of exams. That's rarely, if ever, seen in U.S. The only place in the U.S. where we change filtrations and we do it in an automatic way is in fluoroscopy. That's that last point that you see on the slide, where you have automatically selectable filtration. For instance, if you choose a low-dose mode of operation. How do you get a low-dose mode of operation in fluoroscopy? Well, you increase the kVp. If you increase the kVp, you have more penetration. And usually, you also increase the filtration. So at a given kV, by increasing the filtration, you will get more, you get a lower dose. But now the opposite is, what if you want a high contrast mode? A high contrast mode is just the opposite. A high contrast mode means that your energy has to go in the opposite directions. For more contrast, you got to get less kV. So if you go to lower kV and lower filtration, you're going to have a lower energy beam. You're going to have high contrast. But notice that a high contrast mode means the dose is greater. Oops. That your dose is greater. A low dose mode means that your contrast is lower. So these are opposites. To get low dose, which sounds great, oh, I want low dose, it means that you're also going to get low contrast. When you choose high contrast, that sounds good, but it also means that you're going to get more dose. Okay, so there's the good and the bad of these. I've been talking about filtrations. Usually that filter is placed inside the collimator, and I did want to show you in this particular model. Actually, I got this from the Hahnemann machine. You probably still have them there. On the side, there's a filter slot. You can slip in filters. I don't like that particular model, but this particular model does have that facility. And I think I mentioned that I don't like it because if you rotate the machine, which you would do, the tube, which you would do for an upright chest, you can drop, these filters can drop out. So if I added filtration to meet the minimum somewhere along the line, before I check the machine again, I could have been operating with less than the minimum. Okay? There's that filter slot. Typically, however, the filters are placed between the X-ray tube and the collimator somewhere in this intersection there. Okay. Here's some various other models. This particular machine has a filter dial. You can dial the filter. This little rotating little disc will bring to bear various thicknesses of aluminum into the beam. Very, you know, very much used, as we mentioned, in Europe. Not so well used in U.S. Typically, when I get one of these machines in my department, I ask the engineers to disengage that dial so that you have a certain amount of filtration and you stay with that amount of filtration. Here on the right is a typical portable system where the collimators are much smaller. Those usually will have fixed filtration with no ability to change filtration whatsoever. Okay. How about mammography? We just saw a little while ago that a filter would wipe out a low energy beam. Well, in mammography, that's all we have is a low energy beam. So you don't have that 2.5 millimeters minimum. That does not apply to mammography. The 2.5 millimeters would completely wipe out the mammography machine output. So these mammography tubes are very specially built. They have a window so to allow the X-rays, you know, even the glass would absorb a lot of that radiation. So the portal of the X-ray tube is actually it has a beryllium window. They fuse a beryllium little window into the glass, and typically that's between 0.5 and 1 millimeter of beryllium. Beryllium, remember, is a very, very low atomic number, and it's a very thin foil, 1 millimeter at most. Typically it's more closer to 0.5. And that's to allow the low energy X-ray photons. Remember, in mammography, you want those low energy X-ray photons around the monochromatic peak, at 20 keV peak in molybdenum, and the 23 keV peak for rhodium. Okay, the filter itself, the molybdenum filter for a molybdenum target, notice is very, very thin, 0.03 millimeter. That's a thin foil that we use. The rhodium filter is about the same thickness. What is the minimum filtration in mammo? It is not the 2.5 millimeters of aluminum, as I mentioned. Later on, we're going to be talking about the MQSA. The letters stand for Mammographic Quality Standards Act. Mammography Quality Standards Act. We'll talk more about that when we come to the dose and mammography section. But for now, it's the federal. It specifies the federal minimum, and that federal minimum is just you take the KVP and you divide it by 100, and that should be the millimeters of aluminum half value layer. Okay, but the American College of Radiology for their certification, for their accreditation, they go one step further and they say KVP over 100 plus 0.03 millimeters of aluminum. So that, and that should be the half value layer of the beam. Remember we mentioned the half value layer defines the penetrating ability, and it's the important parameter that combines both filtration and the voltage. So the required half value layers are given by those little relationships. So these are the numbers. So for instance, if you're operating at 26 kVp, very typical voltage in mammography, 26 kVp, I'll go straight to the ACR value. The 26 divided by 100, right, is 2.6, and 0.26 rather, and then add a 0.03 to the 0.26, you get 0.29. Numbers don't have to be remembered, and these little relationships don't have to be remembered. The concept is true, though. You still want a certain amount of filtration in mammography. It's going to be relatively little, but you do want that filtration to wipe out some of those very low energy components of the beam, and so that you come up with some kind of algorithm to determine the required thickness. These are the algorithms over here, and but the concept is the one you should take home with you. You still want a certain half value layer to assure a minimum amount of dose, a minimum penetrating ability of that beam. Okay, what if you overfilter? You put in more filter than you should. Okay, well, if you put more filter than you should, then notice that you're just knocking out output, which means longer exposure times, which means motion problems. Okay, if you overfilter, that means then that the beam is relatively high energy. Effective energy is relatively high. That means you're going to get a hit on subject contrast. If you overfilter and you have to have more exposure times, then your loading on the tube is going to go up. And you may not be able to use the small focal spots. Remember that discussion? Small focal spots give you better resolution, better image quality. But if you are loading the tube down because you got so much filtration that you have to have such longer exposure times and MASs, well, then that's going to affect your the tube loading. It's going to affect your ability to choose smaller focal spots to get better image quality. Okay. I mentioned putting this all together for the three areas. In radiography and fluoroscopy, you already mentioned that the 2.5 is the minimum, and we shoot between 3 and 3.5. We don't want to go beyond 3.5. That's then into the overfiltration region. In CT units, however, when we get to CT, we're going to see that there we go to relatively high filtrations. There we do it not so much for a dose reduction. We do it there to avoid the beam hardening artifact, and we're going to have to talk about that. One of the very popular questions on the boards is, how do you minimize the beam hardening artifact? Remember, the beam hardening artifact is that those black bands between the petrous ridges and skull and head scans. And how do you avoid that? Well, that's due to beam hardening. How is that due to beam hardening? Because along the petrous ridges, where you have a more path within bone, the radiation arriving at points in between the petrous ridges have a higher energy, and as compared to all the other angles. And if they have a higher energy, it fools the pixels, it fools the computer into thinking that since you have a higher energy, that means that you have a greater penetration through those pixels. And the computer is fooled. They say, oh, greater penetration? Why, there must be something like air sitting in those pixels, because air allows for greater penetration. See, in CT scanning, they always assume a fixed energy. And but to get a fixed energy, you have to have more filtration to avoid that beam hardening artifact. We're going to have to discuss that further when we get to CT. But as a quick statement, the way you minimize beam hardening is by adding more filter. Okay, and then mammography, as we just said, you specify not so much the 2.5 millimeters, you specify a given half value layer. And that half value layer is going to depend on the target filter combination and the voltage that you put on the machine. Let's look at another aspect of filtration over here. What if we went right into the X-ray tube? Jump right into the X-ray tube and look at the distribution of radiation as it just emerges from the target. This is what you're going to get. Very surprisingly, you're going to get a straight line. Okay? Emax is going to be defined at a particular kVp, and it's going to be straight line right down to zero energy. Okay? That's inside the X-ray tube. Obviously, we can't use that beam for image formation. Let's now see what happens as that radiation gets through the glass of the X-ray tube. Well, as before, you have the preferential absorption at the low energy component. So now you have this yellow curve where you've knocked out all those very low energy photons. But now the beam has to go through the oil. And the oil then does some more preferential attenuation of the low energy photons. And then it has to go through the collimator. And now you get even more filtration of the lower energy photons. Okay? So the typical curves that we've been giving you, that typical Bremsstrahlin curve, is the result of already the beam going through all these various other components and all these other filtrations afforded by these other components. The typical beam we've been talking about, where the average energy or effective energy is 1/3 of Emax, is already the result of the oops, the result of this progressive filtration that you've gone through. But now the beam hits the patient and starts going through the patient. If you go to the middle of the patient, I'm now going to give you another relationship of energy. The effective energy in the middle of the patient is 1/2 of Emax. See, it was 1/3 of Emax at the surface of the patient, but after the progressive filtration inside the patient, now you're up to 1/2 of Emax. What if you keep on going up in more filtration? Visualize putting a hunk of lead in the beam. What if you put a hunk of lead in the beam? Well, you are going to wipe out almost all of the output, right? And you're going to wipe out all of the low energy photons. So what will finally get through that hunk of lead? Why, only the highest energies have any chance of getting through that hunk of lead. And typically you'll have a distribution that's essentially monochromatic with energies at the Emax, very close to the Emax, right? Because those are the only energies that have any hope of getting through that hunk of lead. So what you're looking at here is this progressive filtration to the point where it's incident on the patient. That's your C curve. And then if you are worried about, well, what kind of energies are there in the middle of the patient, well, then you would go to 1/2 of Emax. Okay? What you take home from this is the idea of progressive filtration, where the energies get progressively greater, and now you've already known about the 1/3 of Emax at the surface, but now I'm adding another take-home a point in the middle of the patient. It's 1/2 of Emax. And here it's shown graphically, where you start out with the minimal filtration, you get 1/3 of E effective. The E effective rather is 1/3 of Emax. And as you go up at the filtration at the mid depth, you get 1/2 of Emax. And as you go to a hunk of lead in the beam, where the beam, this filtration curve, the effective energy will plateau out as you get more and more filtration. And at that point, it becomes monochromatic. When this flattens out, it means that there is no further increase in effective energy, and it's a beam is monochromatic by definition. Okay, fine. That now takes care of those original parameters: exposure time, MA, MAS, KB, and filtration. Let's say a little bit about target atomic number, and I'll just emphasize there the points that are more likely to be on the boards. What happens as you change atomic number of the target? Okay, remember that the target atomic number determines the binding energies of that target material. Okay, as your Z goes up, the binding energies go up. Since the going up in atomic number really means you're packing more protons in the nucleus. If you pack more protons in the nucleus, then the all those protons in the nucleus will exert a greater attractive force on the electrons in the various orbits, and the binding energies will go up. We've already seen, for instance, that with tungsten, remember those numbers: 69, 58, 11, and 1. The 1 never really gets out of the tube, so it's really just the signature is 69, 58, and 11. For molybdenum, it was 19.5 and 17.5. And all the other energies are so low they don't get out of the tube. Okay? And so when you change that target atomic number, you change the distribution of the Bremsstrahlung distribution and the characteristic radiation energies. Specifically, as Z goes up, because you have more protons in the nuclei that exert greater forces on the electrons, when you look at that, affects not only the orbital binding energies, but now how about the electron that's coming in from the target? More Z means a greater force on those incident electrons. Okay, and so you're going to affect the Bremsstrahlung distribution. This is the classical curves that they give you. They may give you a curve here given by the solid, and they'll give you a curve given by the dashed. Compare the two curves. The only way that you can change characteristic radiation energies is only by changing the target material. So the classical question on the boards is they'll give you these two curves and they say, what produced that change between those two curves? And you observe that the change consists of an increase in the characteristic radiation energy, and notice also an increase in the number of X-ray photons. But the more dramatic effect that you should be looking for is the change of characteristic radiation energy. And that is the effect of your going up in atomic number changes the characteristic radiations. Okay? But in general, as your atomic number goes up, notice that you get more output, right? In general, you get more output. Photons are coming through. And it turns out that that is directly proportional. You double the atomic number, you double the amount of radiation output. You'll come back. You'll double, and if you double the amount of radiation output, you double the skin dose to the patient. But just like we saw that changing kV, that increases the penetrating ability, well then you can take that into account and match the same image effect and you get less patient dose. That's going to also be true with the atomic number. And likewise for the image effect, if you have if you go up an atomic number, you have more photons, the quantity goes up, well then your noise goes down. Same kind of discussion as before. Noise always goes in the opposite direction as output, as beam quantity. Beam quality goes up because now you have those higher energy characteristic radiations. You may not have changed the Emax, but you are going to have a change in E effective. Because of the additional contributions of the higher energy characteristic radiations. Right here, characteristic radiations go up. And in general, if the effective energy goes up, well, then the subject contrast goes down. Okay? But the unique feature here is you change the characteristic radiation energies. Okay? Let's go on to, well, looks like we've blown our time. Let's stop there, and we'll pick it up next time with the idea of distance. Any questions before I let you guys go? Well, let's stop there then. Oops. What happened? Okay. And we'll catch up with you folks later.
Thank you.